Today, we are analyzing the electromagnetic efficiency of a magnetic pulse welding system, specifically focusing on the sensitivity of magnetic pressure to changes in the transient electric load. Using SimScale's transient electromagnetic solver, we will sweep through the electrical conductivity of the flyer tube to simulate different aluminum grades or thermal states, which would represent a common scenario of working with different suppliers where variety can happen quite often, right? And additionally, we will also investigate the radial air gap between the field shaper and the flyer tube, which in that scenario, we can represent also a little bit of the tooling, alignment, and the misalignment during actual welding processes. The main results of interest that we are after in this case study are the flux density, the Lorentz forces, and the ohmic losses. With these, we can verify if a particular design meets the desired standards. Moreover, to verify if the system generates enough kinetic energy, one could also extend this analysis by a few analytical approaches, which will not be covered for today. Hi, my name is Khairi. I am part of the application engineering team here at SimScale. Let's dive into our case study. All right, now let's take a deeper look into our case study. So, the CAD model that we are working with today is what we have here represented. So we have a steel coil made of one turn. We have our field shaper, which is made of copper. Now the field shaper's purpose to kind of really help concentrate the magnetic pressure on the areas that matter on the flyer tube that essentially is going to fly at very high speeds and collide with the aluminum target tube and basically invoke the welding process. Now, the target could be made of aluminum, could be made of copper, it could be made of different materials, right? That's one of the main advantages of magnetic pulse welding is that we are not relying on heat to weld the materials, but we're relying on impact and collision speed to melt those materials. And the welding process happens in seconds. There are no dangerous gases that is involved in this process. Now, of course, because we're dealing with very high energy, some of that energy is going to be dissipated as heat. And then in the end, this is something that actually also should be controlled. To kind of understand how this process works, let's take through these figures from bottom to top. So for the coil, we have in the circuit model, we have a capacitor bank. And that capacitor bank has overall, we're providing around 8 kilovolts into this circuit. So we're charging the capacitor, close the switch, and then we send off a very quick impulse of current that has a very high peak of around 618 kiloamps and a duration of 120 microseconds. Now this transient current that is passed to the coil generates a changing magnetic field that is passing through the flyer tube that consequently creates eddy currents in the flyer tube, which has their own magnetic field, and that creates Lorentz forces on the flyer tube that then pushes it down by this magnetic pressure to collide with the target and then finally invoking this molecular level weld in between the two parts. Sounds great. Now, just to reiterate what we're trying to get out of this simulation in relation to both the tooling, alignment, and misalignment by investigating the air gap between the copper field shaper and the aluminum tube, but also we want to vary the conductivity of our aluminum tube to kind of just investigate realistic scenarios of what happens when I'm working with different suppliers and I'm having this grade and that grade, and I need to make sure that my machine is working efficiently for a wide variety of aspects. And for this, we want to extract the flux density, the induced eddy currents, and the Lorentz forces, kind of get an idea about the efficiency of the energy transfer. And moreover, we need to make sure that the material doesn't actually melt during this process. So we also want to investigate the Joule heating in this. And for that, I think now it makes a perfect time to make a transition and take a look at how everything works live within SimScale. Now, I will switch between different tabs and navigate directly to the SimScale website because that's essentially the space where everything happens. SimScale is a cloud-native platform, meaning that you can access it from anywhere at any time in the world, right? So you could be working from your home, you could be working from office remotely, it doesn't really matter. You always have access to SimScale directly from any browser of your choice. Now, when you log into your account, you can navigate to the dashboard. And the dashboard is a data management system that SimScale provides along with its simulation capabilities. In the end, SimScale is a platform that is able to do multiple different things. And part of this platform capabilities is the data system. And here you can manage all of your simulation projects both in a private space, that is your projects, but also in shared spaces that you can interact with your team working on different projects. This could be project A, project B, project C, etc. Right? Now, the main topic for today is, of course, the magnetic pulse welding. So let's make a quick transition to our simulation workbench. What we are seeing in front of us here on the screen is the SimScale workbench, and this is essentially the space where you interact with your simulation model. Everything from CAD import to post-processing is available within the same space. You don't have to jump between different tools and silos to complete a simulation job. Starting with the first step, which is importing CAD geometry. So we work with almost all native CAD formats out there. This could be SolidWorks, Inventor, Creo, CATIA, you name it. Of course, the standard CAD formats, the generic ones like STEP files, are also supported. After you import your CAD geometry, you can go ahead and create a simulation. And here SimScale provides a multiple physics solution, right? So you have everything from flow capabilities, structural analysis, and of course, electromagnetics, which is our focus for today. Now, let's take a little bit of a deeper look into the simulation results for one of the simulations that we've done inside the conductivity study, which in this case, it's the aluminum alloy with 30% conductivity of a pure annealed copper. Now, what we're visualizing in front of us is the transient fluctuation of the flux density magnitude over the flyer tube and the inner rod. This little increase, or let's say significant increase actually, on the flyer tube essentially represents the magnetic pressure within the model. So we have a section of our flyer tube that is outside this region, so not a lot is happening there, but the field shaper helps concentrate a lot of the magnetic pressure in this region, which essentially initiates the impact process on this. What is very important is to make sure that the overall flux density within the air gap, based on the tooling requirements, so for example, what is the overall air gap distance between the field shaper and the actual aluminum coil? That's also a very important parameter here that controls the overall amount of eddy currents that will be generated here and consequently affecting the forces. We can also see that there is a significant amount of shielding between the flux density just before the flyer outer surface and then within the inner surface. And that is because due to the additional electromagnetic fields generated on the flyer due to the initial magnetic field from the coil, we have eddy currents generated, which have their own magnetic field, which resists what have tried to create it. So we have the shielding effects, which also can be termed as electrical shielding in this case. Sounds good. Now, this is, of course, one level of results. You can extract various outputs from here, like the ohmic losses, the field, and the electric current density as well. But what I would like to do is I would like to take a step back and show you how such a simulation can be set up. So when we go ahead and create our electromagnetic simulation, we are the available options for us. We can create anything from electrostatics, magnetostatics, time harmonics, and time transient. And the simulation setup for both, or basically all of the analysis types within SimScale, follows the same structure. You work your way from top to bottom, making sure that you have converted everything into a green checkmark. Starting first in this case with the materials, SimScale provides you with a very comprehensive electromagnetics material library that contains various different steel grades with their BH curves. You have also lots of different magnets that you can also use right out of the box within SimScale. From there, you go ahead and you define your coils, and here the coil kind of just represents the type of coil you're defining, whether it's a stranded coil or open, closed topology, etc. Right? Litz wires are also supported in this case. And basically that's it for the simulation process. We can actually take a look here at a complete simulation setup. So we have our materials defined for my steel, the copper alloy for the field shaper, and the different conductivities that I was varying. So the idea here is to provide that current impulse to the simulation and understand the overall reaction. So what I can do, because we're using a cloud solution, we can really investigate various different designs at the same time. So I can run one simulation here, call it design one. I can go back, vary my conductivity of the steel, of the aluminum flyer, where here I'm reducing overall the electric conductivity from 60% of the pure annealed copper conductivity to 30%. And I can go ahead and start a new simulation. Now, there is really no limit. You can be running 50 simulations at the same time while working on different projects, and you receive an email afterwards with the final outcome. One of the important outputs from here is, of course, the overall force distribution, right? So, for example, we can take a look at the force. We have the time transient force distribution here, which we can download and use this to overall calculate the impact velocity of the flyer tube and so on. Now, on the other hand, this simulation can also be extended to provide the overall thermal response from this process. So we can run a thermal coupling simulation, right? And from here, we can get an idea about whether the flyer tube or the inner rod might have a danger of melting within the actual process. So we know the melting temperature of aluminum is around 660 Celsius degrees. We see here the temperatures from the simulation are reaching up to 450 Celsius degrees. So it means that we are within limits, and which is quite good in that regard. Now, I would like to summarize a little bit the results of this analysis in my final two slides, but just before we get there, I would like to bring your attention to the fact that SimScale provides you with support at any particular stage within your simulation journey. You can get this either with our AI assistant, which have been trained on lots of SimScale material from documentations, tutorials, etc., or you can connect directly with one of our support engineers, which will give you tailored advice on your simulation work, ensuring that you end up with successful outcomes. On the collaboration side of things, you can easily share your project with any particular team member, regardless of their location. So no more data download and data upload and all of that stuff, right? You can simply provide them view, copy, or edit access. Perfect. Let's take a step back now and finalize everything from where we started in our slides. And I want to discuss very briefly the influence of the electric conductivity, right? So what we have here on the table, we have different grades of our aluminum. We have here the maximum total force acting on the flyer. So the more we're increasing the conductivity of our flyer, the higher the force generation is. Although the increase is not that significant, we see overall the reason kind of why it stems from that is the overall magnetic pressure generated here is not basically affected that much. Perhaps with a smaller air gap, we might find more significant outcomes from this, which is something also we see a little bit later. However, one thing we can clearly see is that with the increase of conductivity, we have much higher electric current density on our flyer material, and this means that there will be more ohmic losses. So really the making sure that the material doesn't melt by mistake during this process becomes quite relevant here. On the bottom side, we have a graph comparing the overall flux density just before on the flyer outer surface and the flyer inner surface, as we discussed earlier, kind of really indicating the shielding effect that's happening due to the eddy currents. And finally, here we have a comparison of the influence of the air gap. So on the right-hand side, we have almost 1 millimeter air gap between the field shaper and the flyer, and this yielded an overall total force of around, let's say, 8 kilonewton. On the other side, we have a 4 millimeter air gap that resulted in a total force of 9 kilonewtons, right? And the influence of this kind of can also be seen here in the bottom plots. This is here we're measuring the flux density directly within the air gap. So before it was around 25 Teslas, and now we have an increase by almost 3 or 4 Teslas within this process. Overall, there is lots of outcomes that you can extract from this, especially the time transient data of the forces and so on can be downloaded. Then you can essentially do some analytical calculations to calculate the impact velocity and all of that cool things. Thank you for joining, and until next time.